Good morning, lecturer and friends.
My name is Adisti Diyanti.
My name is Kevin Osea Sutikno.
Today we
will present about
distribution of solute between two immiscible solvents. In this presentation, there are 4 topics that we will explain. The first topic is purpose and theory, the second is materials, rules, and procedure, the third is discussion, and the last topic is conclusion. Starting from the first topic, the purpose of this experiment is to determine the value of the equilibrium constant for a solid between two immiscible solvents and determine the degree of dissociation of the solute in the solvent. And the next is the theory. A covalent compound is said to be polar if it is a covalent compound formed by two different elements and have a relatively large difference in electronegativity values between 0.5 to 1.6, while non-polar covalent compounds are covalent compounds formed by the same two elements and have a difference in electronegativity value that is less than 0.5. Something that distinguishes between them is the electronegativity. Electronegativity is the ability of an atom to attract electrons to the atom to be involved in a chemical bonds. Solubility is a variable that indicates the maximum amount of solute that can be dissolved in a certain amount of solvent at a certain temperature. Based on their solubility in solvent, compounds can be divided into 3 types. The first is soluble compounds are compounds which do not form a precipitate, and the second is solidly soluble compounds are compounds which form a number of precipitate, and the last is insoluble compounds are compounds which will form a precipitate. Solubility factor. The higher the temperature, the higher the solubility, because the molecules in the solution will have a higher kinetic energy so they can faster. The effect of pressure on the solubility of solid and liquids is negligible, and the bigger the contact surface area of the dissolved solid, the higher the dissolution rate of the solid. This is because the surface area of the solid molecules in contact with the solvent molecules will be larger, but the molecules in the solid will be bigger. And the last is the polarity of solubility factors, following the principle like dissolved light. Extraction in general divided into 2 types. The first liquid-solid extraction is a method of separating compounds from a mixture in the form of solid, and liquid extraction is the separated compound in the mixture in the form of a liquid. Titration is an analytical method. The concentration of something in the sample is measured by adding a titrate into a solution containing the analyte. The equivalent scoring will occur during the titration when the analyte has completely reacted with the titrate. In some titration, the reaction product from tend to be colorless. Then an indicator is used to determine the endpoint of the titration with color change. Distribution. If solid dissolved into immiscible solvent, then in each solvent there will be a certain amount of solid with a certain concentration. The concentration of solid will depend on the solubility of the solid in the solvent. According to the Nernst law of distribution, if a substance solid dissolving solvent, for example as A, when conducted with solvent to the solid will be partition between the two solvents, and according to the reaction the following equilibrium below. From the equilibrium reaction before, thus the equilibrium constant can be written as stated above. If the distribution coefficient is large enough, it means that the solid move from the solvent 1 to solvent 2 and also vice versa. The value of K will remain if the molecular weight of the substance in solvent 1 is the same as the molecular weight of the substance in solvent 2. If the molecular weight is not the same, dissociation or association will occur in the solvent. And for example, if solvent 1 is organic solvent and solvent 2 is water, then the equilibrium reaction is as stated below, and then thus the equilibrium constant is set below. And the regression equation as stated below can be obtained by logging inside of the equilibrium constant above, and the value of N and K will be obtained with temperature log C organic versus log C water. Next to the second topic. The materials of the experiment is hydric acid, oxalic acid, sodium hydroxide, aquatic, diethyl ether, and phenol phthalate. And the tools is beaker glass, filler, measuring cylinder, glass funnel, Erlenmeyer, burette, and strain, and the last is measuring pipette. The procedure is divided into 2 stages. And the first step of the first stage is take 10 ml of 0.1 normalic acid solution and put it with Erlenmeyer. And the second is started with sodium hydroxide solution and not the volume of sodium hydroxide used in the oxalic acid preparation. And the last is do the step 1 and 2 for 3 times. And for the second stage, the first step is make solution of acetic acid with a concentration of 0.04, 0.08, 0.12, 0.16, and 0.2 normal for the dilution of 1 normal acetic acid solution. And the second is take 15 ml of its solution and put it into a separating funnel. And the next is add 15 ml of either to the acetic acid solution and square the funnel. And the fourth is take until the equilibrium is reached, then allow to separate with water and air. And the last is square the solution in the water and titrate the solution with the standard base 0.1 normal sodium hydroxide solution with 0.1 normal oxalic acid.
This is the discussion part and will be divided into experiment condition, data and calculation, and result which including discussion about experiment done. So the experiment is done as specific experiment condition which is shown and screen. This is the experiment data and calculation part. First, the valence of sodium hydroxide is 1 because it releases 1 hydroxyl ions and free ionization. Next, the valence of oxalic acid is 2 because it releases 2 hydrogen ions and free ionization. Then, the valence of acetic acid is 1 because it releases 1 hydrogen ion and free ionization. The theoretical sodium hydroxide normality and oxalic acid solution normality as primary standard can be cut by dividing the number of moles by volume and multiplied by valence, and the result is shown here. This is the standardization of sodium hydroxide calculation, and if normality can be calculated using N1V1 equal to N2P2 formula, and the result is shown here. This is the calculation for making series of acetic acid concentration from the division formula, which is shown at the screen. We can determine volume of 1 normal acetic acid needed to make 50 ml of each concentration of acetic acid solution. The data on the table is before extraction, and empirical concentration of acetic acid before extraction can be determined using calculation, and the calculation is using N1V1 equal to N3V3, and the result is shown here. The data on the table is after extraction, where concentration of acetic acid in the water is also determined using calculation, and calculation method is the same as before. And this is the example of calculation step. This is the derivation of formula for calculating C organic. It assuming that initial volume of acetic acid solution is equal to volume of water and the later layer. The formula can be simplified to C initial equal to C water plus C organic. This is the explanation of some variable that is used at the equation above. This is the example of calculation of C organic, and we also calculate the logarithmic value of C water and C organic. This is the derivation of linear equation that is used, and the linear equation is shown at bottom right. Then we make a graph of log C organic versus log C water. By taking linear regression analysis, we can get the slope and intercept, hence value of n and k can be determined, and the value is shown on the screen. Now we will discuss about the experiment procedure, begin with standardization of sodium hydroxide. First, we put the solid oxalic acid into bigger glass, then add some water and stir it. Then put it into volumetric flask and add some water until it reaches the light, close and shake the volumetric flask. Oxalic acid is chosen as primary standard because it has large molecular weight, 126 gram per mole, so the bulk of weighing process can be minimalized, and it's also stable and not hydroscopic. Then we do the standardization of sodium hydroxide to measure the exact concentration of it. First, we take and put 10 ml of oxalic acid solution into an aluminum flask and add phenolphthalein to indicate endpoint. Then do the titration until the solution turns pink. Standardization is done because sodium hydroxide is hydroscopic, so its concentration is easy to change. The color changing is due to the Lefebvre principle. After the equivalence point, hydrogen ion concentration is low, so at phenolphthalein equilibrium reaction, the equilibrium shifts to the right and the pink color appears. Next is determining the distribution of acetic acid between two immiscible solvents. First, we make series of acetic acid concentration by taking some 1 normal acetic acid and put it in the volumetric flask. Then add some water until it reaches the light, or using the dilution principle to minimize the error on viewing process, and shake it. The amount of 1 normal acetic acid needed to make solution with series of concentration is calculated and shown at the table. In this step, we do the titration to get the accurate concentration of acetic acid. The procedure is the same like before, but now the acetic acid solution is used. Then we do the extraction by taking and putting 15 ml of acetic acid solution in the separatory funnel, then add 15 ml of ether. Then we shake the funnel for 1 minute and let it in until it forms 2 layers. Pick the bottom layer, which is acetic acid in water, because water has larger density than the ethyl ether. The bottom layer is taken because later we will enter the solution using sodium hydroxide, which is polar compound, to determine the acetic acid concentration. Sodium hydroxide must be visible in the solution. Acetic acid has polar characteristic due to its hydroxyl functional group, and its non-polar characteristic is due to its short carbon chain. The ethyl ether is non-polar solvent because the electronegative difference between the atoms in one is less than 0.5. Water is polar solvent because the electronegative difference between the atoms in one is between 0.5 until 1.6. Diffusion of acetic acid will occur from water, which has higher concentration of acetic acid, to the ethyl ether, which does not contain acetic acid at the beginning. Theoretically, acetic acid will associate and form dimers or double molecule in the ethyl ether, yet dissociate in water becomes single molecule. In this step, we do the titration to get concentration of the bottom layer solution. The procedure is the same like the standardization titration, but here the bottom layer's solution is used. The value of N octet is quite far from the theory. This is due to intermolecular hydrogen bond between acetic acid and water, and also intermolecular hydrogen bond between molecules of acetic acid, which is very strong and hard to break. There is also interaction between acetic acid and the ethyl ether. This will lead to acetic acid imperfect dissociation in water and association in the ethyl ether. So the value of dissociation degree is less than 2. The value of K is more than 1 and it can indicate that acetic acid concentration in water is higher than the ethyl ether at equilibrium. This is accord with compound polarity concept, which has been explained before. The conclusion from the experiment is the equilibrium constant is 2.23475 and degree of dissociation of acetic acid in water is 0.92574. That is our presentation, and thank you for your attention.